X-ray photoelectron spectroscopy is a technique to analyze the structure of atoms and get information about electronic structure as well as ionization energies. It works by irradiating a sample with an X-ray beam and then quantifying the kinetic energy and number of electrons that are ejected from the material. With this technique, we are able to obtain the chemical composition of various materials. It reveals which chemical elements are present at the surface, such as carbon and oxygen. It informs us about the chemical bound nature which exists between these elements as well. XPS has some advantages and some disadvantages, and we are going to go through some of them in here. The first advantage is that it is a non-destructive method as well as a surface-sensitive method, so it is very helpful to do an elemental mapping, for example. Another advantage is that it provides us with quantitative measurements, and it gives us information about chemical bonding and chemical composition of a molecule. On the other hand, it has some disadvantages as well. So it is, first of all, very expensive technique. Secondly, it needs a high vacuum, and it is a slow process. So it might need a whole night to provide results. And finally, it detects all elements with an atomic number of 3 and above, so it cannot easily detect hydrogen and helium. Let's get into some theoretical background. The way this works is that we have an incoming X-ray, and if it has enough energy, it will be absorbed by an atom, and an inner shell electron will be ejected, exactly as demonstrated in this figure. This phenomenon is known as the photoelectric effect. Because the energy of an X-ray with a particular wavelength is known, the ejected photoelectron has a kinetic energy that can be calculated to be equal to the energy of the incident X-ray minus the binding energy and the work function of the element. So in here, the work function is defined as the minimum energy needed to remove an electron from a solid to a point in the vacuum immediately outside the solid surface. So the electron should be far from the surface. Now, by detecting and measuring the energy of this electron, that is, of course, unique for each element, one is able to determine the composition of the sample. Besides the electrons ejected by the X-ray beam, we detect Auger electrons as well. So what are Auger electrons? Following the photoelectron process, we will have an excited ion. And one of the ways to relax is by having an upper shell electron fall and fill that hole created by the X-ray beam and have the Auger electron emitted, conserving energy. This is actually what the equipment looks like. So let's say we have a silicon dioxide sample and it is placed in a high vacuum, of course, not to forget. Then we focus X-rays on it. These will eject electrons out of the sample, as shown here with these blue arrows, the so-called photoemitted electrons. These electrons come through the electron detector, which you can see here in a U kind of shape. And what this detector does is count the electrons and measure the kinetic energy of those. Now, finally, this energy is represented on a spectrum, where each electron energy informs us about the elements in this probe. This figure shows the XPS spectrum of a palladium probe. On the left side, the intensity is represented with respect to the kinetic energy, and on the right side with respect to the binding energy. A photoelectron spectrum is recorded by counting ejected electrons over a range of electron kinetic energies. Peaks appear in the spectrum from atoms emitting electrons of a particular characteristic energy. The energies and intensities of the photoelectron peaks enable identification and quantification of all surface elements. This allows elements on the surface to be identified based on the unique binding energy each element has. The peak areas on these spectra can also be used to obtain the concentration of the elements on the surface as well. The area under a peak in the spectrum is a measure of the relative amount of the element represented by that peak. So let's get into some more detailed observation. First of all, you might have noticed that the energy axis is inversed. That's because we want to be able to get a clear view representative of the atom structure. So the more you approach the nuclei, or the origin, the higher the binding energy is going to be. So if you look at the right side of this figure, at the utmost right, the emission from the 4p and the 4s levels gives very weak peaks at about 50 and 90 electron volts respectively. The next peak is the most intense peak in here, and it is at a binding energy of around 330 electron volts. This peak is due to emission from the 3d levels of the palladium atom. In addition to that, we recognize the 3p and 3s levels with peaks at around 550 electron volts and 670 electron volts respectively. The remaining peak is not an XPS peak, but an Auger peak from an Auger emission. It occurs at a kinetic energy of around 330 electron volt. In this case, it is meaningless to associate it with binding energy. So as we have seen, the height of the peaks is an indication of how many electrons there are in that energy level. With this method, we can identify elements by comparison, given that most binding energies for elements are already known, so we can compare it in catalogs. So we have just seen how to determine electronic structure of an element to identify it. After the electronic structure in the previous slide, let's have a look at the chemical shift. In compounds where ionic or covalent bonding occurs, the peak position might shift. If we analyze a molecule, we will get binding energies as well. And as you can see in this titanium and titanium dioxide comparison, the binding energies will shift as new bonds form. In this example, we have an oxidation which shifts the binding energy by around 5 electron volts to the left. So, what you need to take away from today is basically how the XPS theoretically works and how to interpret the data of such a spectrum.